Hi everybody. I just want to show you a little bit about what I was talking about with regards to RMS as being an equivalent DC source. So what I have here on the screen is an AC source. So I have this AC source here and it's set to 12 volts RMS, right? And I've hooked up this oscilloscope here. Now I'm using the Tektronix scope, and I have another video for Lab 4 which shows you how to use this oscilloscope. And I kind of like using the real equipment more than just the multisim equipment, because this is a little bit more of an experience of like what you would see in a real lab. But looking at the oscilloscope, if I run this simulation, so I'm running the simulation, you can see my waveform on the screen, on the oscilloscope screen, and notice that the peak to peak, there's the peak to peak range of this waveform, right? And I'm set to 10 volts per division. So if I count this, it's 1, 2, 3.4 major divisions. So it's 3.4 divisions times 10 volts per division. That's giving me roughly 34 volts peak to peak. Okay, and I'm writing all over the scope here, but it's 34 volts peak to peak. So this AC waveform that we've got over here, we've set it to 12 volts RMS. We know it's 34 volts peak to peak, okay, or 17 volts peak. Okay, so when we think about that waveform, let's try to make that symmetrical. This is 17 volts peak. Okay, and so what our definition of RMS says is that the RMS value equivalent to this 17 volt peak to peak waveform is the RMS value that will generate the same amount of dissipated power in the same load resistor. So notice I have two load resistors, both 1K, and I've set this DC supply here to 12 volts DC, because this 12 volts, this 17 volts peak or 34 volts peak to peak being equivalent to 12 volts RMS, should mean that if I put a 12 volt DC supply, I will get the same power across this load resistor here as I do on this load resistor here. And so what I've done is I've hooked up two ammeters. And the thing to notice about the ammeter, so the ammeter is going to measure, sorry, I'm saying ammeter, I mean watt meter. The thing to note about the wattmeter, the wattmeter, is that it has both a voltmeter connection and ammeter connection, right? So we have to get both current and voltage into this meter in a proper way. And so what that means is the voltage can go across where we're measuring the voltage like it normally does, but current has to break the circuit and be inserted within the circuit as an ammeter normally would be. So you notice that that when I hook in the ammeter, my circuit goes through the ammeter and back around to create a full circuit. Okay, so I've actually inserted the ammeter into the circuit, and that's really important. So let's open these ammeters. Ammeters. I keep calling them ammeters. That's because it's very late, and I should not make videos so late. But they are watt meters, and when I open both of these watt meters, what I notice is that I have the same 144 milliwatts on each as dissipated power through each of these resistors. So that means that, yes, a 17-volt peak AC waveform gave me the same dissipated power as a 12-volt DC source. Therefore, this has an RMS equivalency of 12 volts RMS. Okay. Hopefully that that helps a little bit with that idea.